for your introduction, Weera. I hope that by now my first slide is visible and that you can hear me. And if you can't, I'm sure someone will come and tell me. The first thing I'd like to do is to welcome everybody who's joined this seventh webinar today, organized by MRP. We call them the MRP webinar series. And I would also like to thank very much all my colleagues at PT Multibangan Rekatama Patria who organize these events. As I always like to mention, there's a lot of work that goes on in arranging this. I can just sit here and deliver my material, but so much work is done to make these a success. So thank you again, everybody, for all of your work in arranging these. This series of webinars is aimed at geotechnical engineering in general so far. And we've had a variety of topics. And today, this is the first time we're aiming at a specific design situation, which is design of road pavements. I think probably, as many of you know, I'm a geotechnical engineer, not a pavement engineer. But there is a very close interaction between pavement engineering and geotechnical engineering, because of course the pavement is supported by the soils and soil materials underneath. So I need to now get a move on, hurry up with this, because as usual, I have quite a lot of material to present to you today. Some of it possibly well known, and there are some items here which have never been seen before. So it's an interesting mixture, I hope. So we've already seen it's the seventh in the series. Today, looking at geotechnical testing and parameters used in road pavement analysis and design. Here is the full list of the webinar series. We're now in the August one, just on the last day. And you can see we do have some more planned coming along up until the end of the year. We'll be looking at a few things today. I mean, not surprisingly, we'll be looking at the CBR test, which you can see in this image. We'll be looking at methods of testing subgrades. And we'll also spend some time looking at surface testing, plate load testing like this. In this case, using what is called an FWD, falling weight deflectometer, and also using this incredible piece of equipment, which we'll see towards the end of this webinar. So this webinar is by no means intended to be a full teaching text on this topic, but hopefully it'll provide some information about the basics. And I'm going to add a few comments and information from actual test data, which is always helpful to see. As we go along, you'll see little blue boxes appearing like this, which will provide additional information and maybe ask a few questions. So really, this is aimed at civil engineers who have some involvement in pavement engineering. There's also information that might be of interest to more experienced geotechnical and pavement engineers as well. Here's some, like it's called suggested reading. I don't think anybody's going to read the left-hand document, which is the 1993 AASHTO Guide to the Design of Pavements, but there's lots of useful information in that document. But the other one is interesting. This is an FHWA document published a few years ago, but it's actually on the very topic, the geotechnical aspects of pavements. It's a 600-page guide, and I'm pretty sure you can download it from the internet if you're interested. So this is the content today. A little bit of an introduction about road pavements and some of the terminology we use, and then we'll look at index testing of soils and also at the AASHTO soil classification system. Following that, we'll look at resilient modulus testing of soils. Then we'll look at the well-known California bearing ratio, or CBR that we normally call it. Following that, a few words about undrained shear strength and CBR profiling for subgrade soils. Then surface loading tests and correlations. Correlations between parameters are incredibly important in this particular area of engineering. We use them all the time. And I'm not going to have one big list of them at the end. I'm going to introduce correlations from time to time as we go through the material. One item I will not cover today is the topic of compaction and density testing, which is much more to do with QA/QC procedures. And that would be a whole webinar by itself. You've heard already, there will be a little quiz at the end of this webinar, as we normally do, and it's going to be related to some of the material presented, and there are prizes for the winners. So this is an image taken from the FHWA guide, which I mentioned just now, and it's very nice because it summarizes the main elements of what I would call a typical pavement. We have 4 materials there: surfacing, a base course, a subbase, and a subgrade. And there are some words there which I won't read out, which tell you general information about those layers. And what I'm going to do now, I'm going to examine this using what I would call a standard pavement for relatively high traffic. However, please be aware that around the world, there are very many variants on the layers used in pavements, with all sorts of special types of pavements and different arrangements. So I'm simply covering what you might call the basic flexible pavement. And we're going to do this by looking at the pavement with 4 layers, of which the upper 2 are asphalt, so we call them bound layers, and the lower 2 are granular, so we call them unbound layers. And those terms we all see used through this webinar. And underneath, of course, the system is the subgrade. The subgrade is the soil that supports the pavement. So let's look at this typical arrangement. We have a surface course, or it used to be called a wearing course. Then we have a binder course. It used to be called a base course. Those are both asphalt layers. Then we have a granular base. In this case, I'm showing it 150 millimeters thick, and a subbase, I'm showing it at 310 millimeters. So that would be a very typical pavement for relatively high traffic. One thing you'll notice is that the thickness of the layers is increasing going downwards. And also what we'll see as we go along is that the properties of these layers, they will become higher, or they increase as you go upwards. And also it's worth noting that in general, not always, but in general, the maximum particle size of the layers also increases as you go downwards. A few brief words about the asphalt layers. I'm not going to spend very much time on it. It's not really my field, but the upper layer, we call this the surface course or wearing course, has a high skid resistance. And we see terms like HMA and SMA. You can see the definitions of some of those, and there may be many others. Many other terms used for that particular layer in the pavement. And then underneath that, we have the binder course. This one has a high shear resistance. Normally it's an HMA, a hot mix asphalt, which is a well-graded material. And just a few comments about this, that generally the thickness of asphalt layers is going to be fixed by the mix design that's used. And also those layers are often fixed by standards, national standards. So for example, that little image, which you can't really read, but it's showing you a series of requirements for the asphalt layers and pavements, in fact, for Germany, depending on the class of the road. Then what's going to happen is that the layers underneath will be designed to support those upper layers. Sometimes we use an asphalt treated base rather than a granular base. We call that often an ATB. And this rather nice picture shows you how the grading of the layers will be becoming coarser as you go down through those layers because they are becoming thicker. So back to our typical pavement, the granular base course is generally the main bearing layer. And this is going to be an extremely high quality processed aggregate. Sometimes it will be replaced by maybe a cement treated base or an ATB. And in that case, there may be differences in the arrangements of the layers, but that's not the purpose of today, to look at that. And then the subbase, this is going to be also a reasonably good quality material, but lower quality than the base course. And it could be a processed material, or in other words, a crushed material, or it could be a natural material if you have a good enough material available. So as I mentioned, properties increase on the way up through the layers. And here I'm just going to put against the layers some typical properties that are coming from what is called the well, it's the AASHTO standard, and they were developed during what was called the AASHTO road test. And the main value there, this A value, is a layer coefficient. You can see them there, A1, A2, A3 in the different layers, and they are related to other properties, or they can be. So today I'm not going to talk about the A values, but I am interested to talk about the other properties which we can see there, like MR resilient modulus, and of course the CBR values. The units of the A values are per inch, if you need to know that. So you need to use the thickness of the layers in inches when you use them directly. Sometimes we have particularly poor subgrades. And in that case, we may well add an additional lower layer, can sometimes be called capping. Sometimes it's called subgrade replacement. It depends on the country and the terminology used wherever you are. So to the main topic today, those layers which I've highlighted there, these are all essentially soils or soil-like materials, so that geotechnical testing and geotechnical parameters are appropriate when we classify and use these materials in our designs. Just one other brief word before I move on is to talk about the term flexible pavement and rigid pavement, because there is an important difference here. Here's a very nice image, and I have to say that a number of my images are taken from the internet, and whoever made them, I'm very, very grateful. I would like to acknowledge the help they provide in giving us this kind of information. But there is a typical flexible pavement carrying a wheel load, and here is a rigid pavement. Now, the rigid pavement has a concrete surfacing rather than asphalt. And one of the big differences there is the way load is spread through that upper layer. So asphalt is much more flexible, so that the stresses directly underneath are going to be much higher beneath the wheel. And that's why we need to have those additional aggregate layers to spread that load further to reduce the contact pressure on top of the subgrade. Now, this doesn't mean you don't need to have supporting layers for rigid pavements, but generally they're not so thick, and they're not necessarily incorporated directly into the design, but they definitely are in flexible pavements. So back to this general cross section, and there are our layers that we're going to talk about: base, subbase, and subgrade. And I've written against them now some properties that we might be interested in, and they're quite similar for each layer: particle size distribution, plasticity index, PI, in other words, the Atterberg limits, CBR, California bearing ratio, then the stiffness properties, E and Poisson's ratio. And then in the upper layers, phi dashed might be a property you need to know about, for example, in some design methods for working platforms. And then in the subgrade, one very common property we want to know about is the undrained shear strength, which is written down there as SU. Now, the phi dash value, that was discussed in detail in earlier MRP webinars, so I'm not going to talk about that again today, but I'd like to talk about the other properties that we see here. And then there's another kind of measurement which is really interesting and important, and in fact it's the basis of design methods in many places, which is to look at the surface stiffness of either on top of the layers or on top of the subgrade. And we'll come to that also later on in this webinar. So let's talk a bit about index testing. Now, the majority of these slides and images are taken from our first MRP webinar. So I shall be reasonably quick going through this, but there are a few places where I'd like to just spend a bit of time talking in more detail about this. So measuring particle size is normally done with sieves, like we see here, using a nice piece of equipment that shakes the sieves to help distribute the particles. And this is used for the coarser soils. That's to say the soils down to, depending on where you are, either 0.06 millimeters or 0.075. In other words, this is for testing sands and gravels. And when we do this, we have this nice little table where we can write down the various names of soils based on their particle size, going from the very biggest ones, boulders and cobbles, down through gravel sands, then to silts and clays. And we have a range of particle size there, which I'm not going to read through. But When it comes to the gravels, sands, and silts, they're also subdivided. So we get coarse, medium, and fine in each of those divisions. And you can see the range of particle sizes written there. So above the red line, we refer to as the coarse soils. And below the red line, we refer to these as the fine soils. And that is particularly important in pavement engineering. Those are important distinctions to make. And I put some typical examples here of three soils, a green soil, a brown soil, and a blue soil. And one way to look at this is, as I've done here, we look at the percentage of those particular particle size ranges. But the nicest way to do this, of course, is with a graph, which we call a particle size distribution curve, or sometimes just PSD for short. And I've drawn on there the blue, brown, and green soils. You can see we have a uniform fine sand, a well-gridded sandy gravel, and a uniform coarse gravel. So we can see that the names from the soils are coming from these particle size curves. Another important, some more important terms, again, particularly in pavement engineering, are the uniformity. So we have a uniform material in the top picture there where all particles are much the same size, which is not so good for pavement construction. And then in the lower picture, we have a well-graded soil, which has a wide range of particle size. And that's what we're normally looking for in a pavement construction material. Then there's also angularity. In this case, the top picture is a crushed limestone material, very angular, as you can see. Those are ideal for pavement construction materials. The lower one, those are nice rounded river stones and a very rounded material, much more difficult to use. Normally, in fact, you need to run it through a crushing machine to get some split faces before you put it into a pavement. Now let's look at the finer soil. So this is the same tabulation. We have a green, brown, and a blue soil again. And again, I've shown the percentages of the various soil types. The green one, it has some fine gravel, but goes all the way down to silt, whereas the blue one is entirely in the silt and clay ranges. And again, much easier to visualize this with the particle size curve. And again, you can see there the green, brown, and the blue soils. Now, we can measure this particle size information using sieves only down to the lower end of the sand range. And we can also add information about descriptions of angularity, and that gives us a very good description of soils of that type. But below that, we get into the finer soils, and we can measure particle size. We have to use a different technique. It's a more complex and more difficult test method, probably generally more expensive as well. But to be honest, sometimes not so useful. And it's more useful to actually look at the behavior of the finer soils using the Atterberg limits. Now, having said that, there is one big exception, and it's an exception to do with a situation where you might be looking at expansive soils in your subgrades. Now, we had a very, very good presentation about this from Professor Jorge Zornberg via ENA IGS earlier this month. And he talked about a property called activity. Activity is the ratio of the plasticity index to the clay fraction. And if you want to look at activity, then you would need to carry out a particle size distribution test within the fine soils. Another important point to remember here is this dotted brown line is the 0.425 millimeter limit, because when we do Atterberg limit tests, we only do it on the material finer than that particular line. So we have to remove the coarser particles. Let's talk a little bit about clay. Now, clay subgrades, really, that's the main topic today. If you have nice granular subgrades to build pavements on, you're not going to have much of a problem and your pavements will be quite thin. But the bigger issues come with clay subgrades. And so they are generally more critical in pavement design and construction. So we will concentrate on them today. Now, the Atterberg limits are these very useful little numbers. And the way to describe them is like this. If you had a lump of clay in your hand and you start to mold it, when its water content is low, you'd measure quite a high remolded shear strength, undrained shear strength. And we would find a particular water content called the plastic limit. Of course, the test method I'm not going to talk about today. You probably all know about how we do the test, but as you start to increase the water in your sample and you keep molding it in your hand, it's going to feel softer and softer. And eventually it's going to pretty well flow out through your fingers. And at that stage, we've reached what's called the liquid limit. And that range between those two is what we call the plasticity index. We sometimes refer to those as PL and LL. It depends on your preference, but those little numbers are very, very useful when we're looking at these clay materials. So here's a couple of nice pictures. The upper one is some kind of very, very fine material that's in a sludge lagoon, and it's pretty well at its liquid limit. It's flowing. The lower one is a compacted clay fill, probably close to its plastic limit. And the way we plot this data normally is on what's called a plasticity chart or a Casagrande chart, where we plot the plasticity index versus the liquid limit. And this plot is very, very useful. And part of that plot will be this line called the A line. And the A line divides essentially the clays from the silts. And then we can further divide them into the low plasticity and the high plasticity. And there are more complex methods of doing this. And you can see there are two quite different soils: London clay, which is a highly plastic clay, and a glacial till, which is of a much lower plasticity. So what I'd like to do now is to look briefly at the AASHTO soil classification system, which is a particularly relevant one because it's aimed at pavement materials. So here is the main distinction between the materials. So we divide materials into either principally granular materials or principally silt clay materials. And the boundary between the two is 35% of fine material. So if you've got 35% or more, it'll be in the silt clay category. If it's less, it'll be classed as a granular material. And then we have these terms, A1, then A3, A2, A4, A5, A6, A7, which are the classifications we put against the various soil types. They are subdivided, A1A, A1B, etc. And then the A2s are all subdivided, and A7 also subdivided. Now, the main distinctions are coming from particle size, and the way I've tried to describe it in a slightly different way to the way you normally see it. So we've got the amount of fines, that's the content of fines, and then we've got the 425 micron limit in the middle of the sand range, and then gravel. But I've switched gravel over to be a minimum value. In other words, it's the percentage retained on a sieve, because that means an A1A soil should be 50% gravel or more. Anyhow, that's just a summary of the requirements on particle size. And then we can add plasticity. You can see that the A1 soils can be very slightly plastic in their fines, A3 non-plastic, and then the other ones would be more plastic materials. And these would be the typical names that you'd see for these kinds of soils. So the top ones are gravels and sands. Then the A3 is specifically for those uniform fine sands, things like dune sands and some beach sands. And then the A2 soils can be things like silty or clay, gravels and sands. And then finally, when you get down into the finer soils, we've got the silty soils and the clay soils. In terms of their general quality, as road building materials, they range from excellent down to good as we go down the list, and then further down from fair down to poor. So this is one reason why I think that the AASHTO system is very nice for these materials, because it is related to their quality for use in road pavements. Just to show you how the plasticity chart works for the AASHTO classifications, it's the same basic diagram of plasticity index versus liquid limit, but the division lines are the fine red lines you can see there. So this is the subdivision of the A2 soils. So you can see there you've got A24, A25, A26, A27, and it depends on where the fines, where the plasticity of the fines fits into that arrangement. And then for the fine soils themselves, the silty soils and the clay soils, the divisions are similar: A4, A5, A6, A7, with A7 subdivided into A76 and A75, where A76 quite simply are the most difficult soils. The highly plastic ones above the A line. The A line is also present there, the thick brown line. So you can see very nicely how it works. And you can see how London clay is now appearing in that A76 category, whereas in the previous slide, the glacial till was appearing down there in A24 and A26. So just to make one last point here is that in webinar number 1, I spent rather more time talking about some of the important aspects of measuring the Atterberg limits, particularly from the point of view of preparation of samples. If you want to know more, then you would need to review that webinar number 1. So if you've got some classification testing data like this, then this is the information that you need to make your classifications according to the AASHTO system: plasticity and various limits on the gradings. So that's pretty well all I want to tell you about the index testing and classification. But I also want to just spend a couple of minutes on a particularly important point, which is looking at the interface between the granular soils and, in this case, the finer subgrade soils. And in particular, I just want to look at this issue of, will you get mixing across that boundary due to ongoing loading from wheels or trains or whatever it is you're designing above that pavement? And this particular issue, we sometimes call it pumping, where you get a mixing of the fine soils into the coarse soils. This is actually quite a long discussion, but I thought I would just show you very briefly one aspect of the index properties which is useful in looking into this. And to do this, you need to have particle size distribution for both layers, and the plasticity data for the subgrade would also be useful to know. So we're interested in this. If this is a kind of enlarged view now of the circle I had just now. And what we're interested is in the question, can the fine subgrade soil at the bottom move up in between the coarse particles in the aggregate layer above? And we do this by using what are called filter rules. Now, here's a very nice picture. Actually, that piece of rail track is in Jakarta, and you can see how we have intense pumping going on. We actually have silt material up at the top of the railway ballast. So that's the result of extreme mixing between the two. Now, we check this out using filter rules, and I just want to mention them quite briefly, where we need to look at the particle size curves, in particular what's called the D15 of the fill and the D85 of the subgrade. This will become clearer when we look at this diagram. So here is a particle size distribution curve for the subgrade in brown and for the fill material in blue. And we can identify on here the D85 of the subgrade, you can see it there, and the D15 of the fill, about 10 times greater in this particular example. So what we're interested in is that ratio between those two values. And we are lucky that in the past, people have done research into this, and they've looked at the stability of that interface. And in this particular graph, we have D15 of fill plotted against D85 of the subgrade material. And I've written on there the names, silt, sand, gravel in each particular case. And all of those particular combinations there with the solid symbols, they had an unstable boundary. But there's some further data here with the open symbols, and in that case, the boundaries were stable. They didn't permit mixing across the boundary, and you can see it's really quite well defined. And in fact, the inclination of that line that I've taken through where they meet the two lots of data is a value of 8 when it comes to that ratio. So based on that, as long as that ratio is less than 8, then it's unlikely you're going to get mixing. But to give it some additional, if you like, safety, then we normally limit that ratio to 5. And that's often referred to as the filter rule according to Tensar, and it's called the piping criterion. This issue tends to be of the biggest problem with silty subgrades. Anyhow, one of the important uses of this approach is to answer a common question. Is it important to use a geotextile separator at the bottom of my pavement? Commonly, we do use them because commonly we have a problem, but this particular procedure is one way of checking. Now, big change of topic. Let's talk about soil modulus. And there's a nice picture there of a triaxial test. I've used this particular image before in previous presentations. So I'm not going to spend too much time talking about the details of the triaxial test. It's a loading test of a cylindrical specimen, and we apply a cell pressure around the outside of it, and then we load it with the deviator stress on the top. But I just want to talk about a few of the features of this. So let's just remove the specimen by itself, make it look like a cylinder, and then apply a stress on the top. Now, when we do that, what's going to happen is that the sample becomes shorter and wider. And the shortening is given, we term it strain. So that's the strain that we can see there. And the outward expansion is also a strain, but it's given by the strain, the vertical strain times Poisson's ratio, but it's negative in the sign convection that we're using here. And this Poisson's ratio is a very important little parameter which describes the reaction in the opposite direction, or the direction normal to the loading when you load a material. This is very basic information. We learned about Young's modulus and stress over strain a long time ago. But I just wanted to make a few little points about this. This Poisson's ratio in soils can range from something close to 0 up to 0.5. And other materials you can see there, steel, rubber, and cork. Now, the reason I mentioned that, there's a bit of trivia here. In fact, cork has a Poisson's ratio of 0, whereas rubber is 0.5. And this is why stoppers or corks that we put into bottles are made from cork and not rubber. It would be very difficult to pull a rubber cork out of a bottle because it would expand as you pull on it, whereas cork doesn't. When it comes to other engineering materials, concrete, asphalt, aggregates, dense sand, fine sand, I've listed some typical ranges of the Poisson's ratio there. Particularly in saturated clay, because in the undrained condition, we assume no movement of water out of the clay sample, then Poisson's ratio is normally assumed to be 0.5 in that case. So there is another form of loading. Let's go back to this image where we could do this loading inside a rigid tube and do the same test. So this means that the soil sample can't expand. So we apply sigma again, the soil becomes shorter, and we're going to call the strain in this case epsilon c because it's constrained. And we can then, again, we can calculate a modulus, which we call M. It's a constrained modulus. And provided Poisson's ratio is greater than 0, then M will be greater than E that we calculated previously. And of course, because it's constrained, the horizontal strain must be 0. In fact, this is the condition of the odometer test that we use to look at compressibility of soils. So sometimes this is called the odometer modulus. However, there's another way we could arrange this. Rather than have a rigid tube, we could apply a cell pressure and arrange that the cell pressure also makes sure we get a horizontal strain of 0. And in this case, the cell pressure would be given by this relationship. It would be equal to the applied stress times Poisson's ratio over 1 minus Poisson's ratio. And because of this, we can then calculate a relationship between M and E, which is given by the expression that you see there. And in this little table, I've given you some typical examples. Of course, with cork, because Poisson's ratio is 0, then M and E would be the same thing. But in an aggregate, where you have a typical Poisson's ratio 0.35, then you can see there is a significant difference. But one important point about this discussion is that you can see that depending on the cell pressure or the lateral pressure you apply in a test, you're going to get a different modulus. So M will be different. If I use different values of the cell pressure, I'm going to get different values of the modulus which I measure. And then there's another additional slight, let's call confusion or addition to this behavior, is that when you do a test looking at axial stress against strain for a typical soil material, it's not linear. It'll be something like the graph you see there. So this means that the modulus that you measure is going to depend on the strain level or stress level. So we have two complications, that when we measure modulus, particularly of granular materials, it's going to be very much influenced by both the confining pressure and the stress level. So this is something we want to look at. And we're going to do that by looking at a test method called a repeated load triaxial test. So we're now going to talk about what is called the soil resilient modulus. A resilient modulus means recoverable modulus, essentially the elastic one that is going to be there after you've done a lot of loading. And we'll talk about it in terms of a particular test method given by the reference there. It's an AASHTO standard. There is a sample being prepared for this test, and there is an arrangement of equipment. Now, the equipment to do this testing, I'd have to say it's relatively complex and expensive, and probably these tests don't get done very often. There is the setup for a larger size aggregate, so it's a bigger piece of equipment. And we call this the repeated load triaxial test. You might call it cyclic load, but it's not quite right. It is a repeated load triaxial test. We'll see this in a minute. So let's go back to our diagram and understand a little bit about this test method. There are other standards apart from the AASHTO one, but I'm going to use the AASHTO one. It's quite commonly used. And normally in this case, the cell pressure is applied by air pressure because it's a fast test. And there are two different procedures of testing, depending on whether you're testing the granular base and subbase material of a pavement or the subgrade soil. So I want to just tell you something about the differences in these procedures. Now, when we apply the deviator stress, that's the stress on the top of the sample, it's applied in a kind of waveform that you see below, where you have a background stress, which is 10% of maximum, and at a regular interval, you increase the stress and then decrease it again. And that's the maximum stress value. So what you can see here is that the test is essentially modeling pulses of load that you'd expect to get from traffic. And that's why it looks like that. So specimen sizes depend on the material you're testing. So for subgrade soils, especially cohesive ones, you would use relatively small samples. But when you get into the coarser subbase and base course materials, then you need to have a larger specimen, up to 300 millimeters diameter. And there's therefore a limitation on maximum particle size, normally limited to 25% of the specimen diameter. So there is a limit then on the maximum particle size you'd be testing using these procedures. Now, the basic test is done in 16 stages. So there's an initial stage of between 500 and 1,000 load applications, which is to condition the specimen, to kind of, if you like, to do that initial rearrangement of particles to get it into something closer to its long-term state. Then once that's been done, we have 15 stages, and each of these stages has 100 load applications. And we determine the modulus as an average of the last 5 load applications of each stage. And then in each stage is defined by its cell pressure and its maximum deviator stress. So there's an image of one of the final cycles in a test, deviator stress versus strain, and we take the slope based on the unloading part of that part of the curve. There are some various stress definitions which get used in this kind of testing, and there's quite a long list there. And you have the general case when all 3 principal stresses are different, and specific case of when sigma 2 equals sigma 3, that's to say for a triaxial test. I'm not going to read through all of those, it's there as a reference, but the two that we will be using in this testing are the deviator stress, which is the difference between the major and minor principal stresses in the triaxial test, and also the bulk stress, which is simply the addition of all three stresses. Those are the two we're going to be seeing as we go through the data. So here is a tabulation of the loading procedure for subgrade specimens, so that's finer soils generally. It'll be done at 3 different cell pressures with an increasing deviator stress in each case. So you can see there, I've written down the 16 stages, but I've called the conditioning one stage number 0. And in each case, you'll see there is a value for the confining stress, sigma 3, the maximum deviator stress and the bulk stress that comes out of that, and the number of load cycles. So I'll just show you what they look like. This is not a just interesting piece of information, but we'll look at it in a different way in a minute. So that is the first group of loadings where we have a particular cell pressure. Then we increase the cell pressure and do a second group of loadings. And then we increase again the cell pressure and do a third group of loadings. And I'd have to say, looking at that, it's a bit difficult to see what's going on. So because I'm a geotechnical engineer, my first thing to do here is to plot this on a stress path diagram, which looks like this, where we've got the mean shear stress against the mean applied stress, sigma 1 plus sigma 3 over 2. And I've put on there in the blue lines and purple lines the various stages of the test. So 0 is the conditioning one. So in other words, the load is cycled between the 2 large square symbols in the conditioning stage. And then we have 1, 2, 3, 4, 5. Then we have 6, 7, 8, 9, 10. And finally, 11, 12, 13, 14, and 15. And when you see them like that, they make a bit more sense. I've also put on this diagram the 5 values of 30, 35, and 40 degrees. And what you can see with this particular test is that for subgrade soils that the loading stages are getting closer and closer to failure. And in fact, if you're testing granular subgrade soils, you don't normally carry out stages 14 and 15 because the sample will probably fail anyhow. So now here is the same table again, but I've now, for a particular test on a particular soil, in the right-hand column, I've put a list of the measured resilient modulus values, and they're written there in numbers. And again, not the nicest way to look at it. So let's look at it as a graph. So here is a graph where I've plotted resilient modulus in megapascals versus the deviator stress. And the deviator stress is on a logarithmic scale because it's just nicer to see things in that way. And it goes like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to 15. And you can see what's important from this is how much that resilient modulus is changing depending on the loading condition. So generally, for subgrade soils, resilient modulus will be higher for low deviator stress. It's cycle number 1. So now let's move on to the coarser soils. Similar procedure for the way we test subbase and base materials. There are some differences though. We now have 5 different cell pressures, and we do it like this. So we have 3 values of sigma 3 there in that group, and then a higher cell pressure, higher again, and the final group. And again, written down like that, not particularly easy to take in. So again, I'm going to put it onto a stress path diagram like this. Now much easier to see what's going on. So we have the conditioning stage there with the large brown symbols. That's stage number 0. And then the loading stages go like this. 1, 2, 3 is now at the low end. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what you'll see now is that continually through the test procedure, we're going to a higher and higher bulk stress. And in fact, in this particular case, the most critical stage is generally stage number 9. That's one getting probably closest to failure. And we'll see that on the next slide. Now, This next slide, I was lucky to find this. I mean, again, this is something I borrowed from somebody on the internet, and I'm very grateful for finding this and acknowledge the work they do. But this is such a lovely picture because it shows you an entire test in one diagram. Axial stress versus axial strain on the horizontal axis. And each of those kind of bunches of curves of similar height is one of the stages. And you can see there highlighting where is sequence number 9, and you get the most strain going on because that tends to be the critical one. And then even nicer, this person also has the same diagram showing the last 5 load cycles from each stage. So MR, the resilient modulus, is the inclination of each of those little groups of curves, the average inclinations. And you can see how they are getting steeper as you go down the sequence of loading. So now if we plot those, sorry, there are some numbers. You can see if you look at that sequence of numbers, MR in the right-hand column in megapascals, 121.1 for the first stage, and then going all the way down to 451.6 for the last stage. So first of all, you will notice this huge variety of resilient modulus values depending on the stress condition in the test. And again, a nice way to look at this is plot it like this. So this is the same data plotted as resilient modulus. It's now on a logarithmic scale against bulk stress again. And it normally comes out in something remarkably close to a straight line. So you can put a relationship on that of the form that resilient modulus equals a constant times the bulk stress raised to another constant. And you'll find those sorts of relations published. If you look around for them, you can find that very often for all sorts of different materials if you want to get some assessment of resilient modulus of a material that you're using. Sadly, I don't think many laboratories do this testing. I don't know if in Indonesia there are any laboratories that can do resilient modulus testing of coarse materials, but luckily there's plenty of correlation around, and it's the correlations we often rely on to get these sorts of numbers. I can compare that to the subgrade. Oh, sorry, just to show you where the stages are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then compare it to a typical subgrade material. Now, please notice as I go from one to the other, it appears that the subgrade material is stiffer, but the resilient modulus axis is 10 times smaller. So in fact, it's very much lower modulus. You can see that modulus axis is going from 10 to 100 on the vertical axis. This one's going from 100 to 1000. So very, very different. So I hope that gives you some insight into this resilient modulus and how it is measured. Its application is interesting. Here is a little table that is showing you for typical pavements where we have asphalt thickness across the top in millimeters, so from thin asphalt to thick asphalt, and the column on the left is the base of the granular thickness, 100 millimeters down to 300. Then the number in the table is the bulk stress calculated at the midpoint of the layer. So you can see that, and this is the bulk stress assuming loading from a standard tire. So you can see that, so it is due to the loading from a wheel, which we're designing for. So you can see that with a thin asphalt and a thin base layer, we get a very high bulk stress. But down at the other corner, with a thick asphalt and a thick base material, we have a very small bulk stress. So this means that our MR value is also going to be varying very much. And to give you an example of this, here is a tabulation coming from the Ostrodes Pavement Design Guide, which is giving you a table of resilient modulus values for what here are called normal standard granular base materials. And again, it's in a similar way. We in this case, we have the modulus of the overlying asphalt layer on the horizontal part of the table, and the vertical part on the left side is the thickness of the overlying bound material. And you can see then that the we have quite a big range of this is the resilient modulus. The numbers in that table, upper value of 350 megapascals, going all the way down in the far lower right corner, lower value of 150 megapascals. That's for a normal standard material. There's a similar table here for a high standard, very high quality base course material. Similar arrangement, but in this case, those modulus values are higher. So that's just showing an application of this in a real design method. Now, a few words about CBR. Moving on to CBR now, the California bearing ratio. This is a term or a parameter that gets mentioned a lot when we're doing pavement designs and calculations. And I'm sometimes not quite sure if people know very well what the CBR test consists of. So what it is, it's a test where we load a sample with a 50 millimeter diameter plunger. So it's a penetration test, basically. You can see some nice pictures of some nice clean equipment there. So we measure load versus settlement. So that means it is quite well related to stiffness. So here's a cross section of the test. You can see there the plunger in the middle of the sample. The sample has a diameter of 150 millimeters and the plunger 50. So it occupies the middle third, and we place weights around it to imitate, if you like, the load of the pavement construction materials above. We load at a certain rate, and we carry on until a 10 millimeter penetration is reached. There is also a limit on particle size even in this particular size of mold, 90 millimeters. So we then get a graph, and the typical result would be the dark brown result, which is force versus penetration. And normally there's some bedding in at the beginning of the test. You can see down there at the bottom. So that's corrected to get a smooth curve that goes down through the origin. We then identify the force on the plunger at a 2.5 and a 5 millimeter penetration. So they're called F2.5 and F5. And we compare those with some standard values, which happen to be 13.34 and 20.02 kilonewtons, which come from testing a standard crushed limestone material. And that ratio is therefore the CBR. So it's a ratio given as percentage between the measured value and the standard value. So CBRs of 100% are perfectly possible. They would be very high quality road-based materials, but all the way down to clays, where we can quite happily have CBRs of 1%, which would be very soft. So the CBR test is like a miniature plate loading test, but at a CBR of 100%, the stress underneath the plunger is huge. It's 10,000 kilopascals or 10 megapascals, enormously high. So it might be a stiffness test, but it's going up to very, very high stresses. So it is approaching failure. If we look at it for the case of clays, say we have a CBR of 1%, which would be, and that would mean the load under the plunger was about 100 kilopascals of the stress. Then a 1% CBR is similar to an undrained shear strength of 25 kilopascals. And if you do a quick bearing capacity calculation with, say, an NC of 5.14, you'll see then that the clay is quite close to failure. So it is approaching failure. So this is if you like, a modulus related test at very high stresses. And one common question is, what's the relationship between CBR and undrained shear strength? So there's no one answer to that question. So let me show you some data here from two quite different materials. London clay is a very common subgrade, obviously around the London area in UK. And there's some very well-defined data there. This is plotting CBR against undrained shear strength. And the lines there are giving you relationships of either 20, 25, or 30. And the other data there, the dark brown dots, are a glacial till, quite different material. We saw it earlier on the Atterberg limit chart. And you can see that why there is no one answer. Commonly, people use a value of 25. Sometimes they like to use 30. But you can see it's really quite important that you establish this if you need to know it for your particular conditions. One thing that's sometimes done with CBR testing is having compacted your sample into a CBR mold, especially a clay. The CBR value can be enormously high on a freshly compacted clay sample. You get 20, 25%, no problem. But of course, clays are often going to be subjected to the effect of water during their service life. So to imitate that, we carry out what are called soaked CBR tests, where we put the sample into a water bath. It can be up to 4 days or even longer, depending on regulations in a particular area. And then we do the CBR test afterwards, and we call them soaked CBR values in that particular case. A few words about correlations with resilient modulus. Now, the famous one given in AASHTO is very simple one to remember, is that the resilient modulus approximately 10 times the CBR value in megapascals. That's intended for fine-grained soils up to a CBR of 10%. And I've drawn the relationship actually going past CBR of 10% in the graph. You can see it there. It's a very simple relationship. There is another relationship very popular that people like to use, which gives you a slightly curved result. It's the sort of yellowish colored line there. This one is published in a TRL guide, LR 1132. Also intended for CBRs in a particular range, you can see there, and for subgrade soils. Sometimes designers like to switch from one to the other as you go past a CBR of 10%, which is a slightly bizarre thing to do, because if you design your pavement for a CBR of 10%, when you reach 11%, your pavement becomes thicker because your CBR, also your MR becomes lower if you use that approach. But anyhow, that just to be aware of that. There's also the potential for doing CBR tests in situ. Same basic equipment. You can see an arrangement there using a vehicle as reaction. And sometimes people like to do these. They probably work quite well on very consistent fine soils, but they can also provide or give some very variable results. So it's very important to do a general check. Now, I just want to show you something about some published relationships between CBR and the plasticity index, also taking into account water. These are coming again from that same TRL report I mentioned earlier on. And this is all to do with the condition in the subgrade after you build a pavement, and the suctions in the subgrade soils reach an equilibrium condition. So I've just got a few slides to try to explain what I mean by this. So here we have a nice field with a cow standing in it, and we're going to build a pavement over this. The water table is at a depth of 2 meters. So that dotted line would be the hydrostatic water pressure profile. And above the water table in a clay, if there's no flow, it'll be negative. In other words, you have suction in the clay above the water table. Now, if the sun comes out in the summertime, then you will tend to get evaporation. So you'll get an upward flow and you'll get quite high suctions, which is one reason why the cow finds it very easy to walk around, because the clay becomes nice and stiff. But there's another situation when it rains a lot. If it rains on the field, then you tend to get water ponded on the surface. So you will reduce the suction to 0 at the top, and you'll get a profile something like that. So you can see, depending on the conditions before you build your pavement, the suction within the subgrade soil can be anywhere between, say, here and here. And this can have quite a big effect on what happens when you build the pavement. So we place a pavement over the top. Now, you would start off with your original condition, but what's going to happen is that the pavement essentially seals the surface and prevents either ingress of water or evaporation when the sun comes out. So you'll end up essentially going to something close to hydrostatic. So this means that if that's the long-term equilibrium condition, then if you have a high water table, your suction is very low. If you have a low water table, your suction becomes much higher. So in the tables we're about to see, you're going to see that this is an important feature of assessing the results. So this is coming from that TRL guide. So for different soil types in the first column, from heavy clays, with you can see the plasticity index there, all the way down to coarse soils, we have CBR values depending on whether it's a high water table or a low water table, taking into account the construction conditions: poor, average, good. For example, poor would be after lots of heavy rain, good would be after a nice drying season. And you can see this has an effect on the expected long-term CBR after the clay has come into equilibrium and the suctions have come into equilibrium. This particular table is for thin pavements. That would be quite thin, up to 300 millimeters or so thick, total thickness. And then there's a second series of values for thick pavements, which would be total thickness of 1200 millimeters. And the red figures are the ones that have changed. And for some thickness in between, you could interpolate. But this is one way of giving you an indication of likely long-term CBR values underneath pavements, depending on these conditions. There's a lot more information provided in the guide itself, well worth looking at if you want to get involved in this. One other useful investigation you can do when you're looking at CBR is to do a compaction test in the CBR mold, where we all know about the compaction test, where we keep changing the water content of the specimen and we compact it, but you can do that in the CBR mold. There's more work to do because there's a bigger volume. But what you can then do, because the CBR mold specimen is quite big, you can test it in different ways. So in this particular case, tests were carried out to measure the undrained shear strength for these different conditions. And you can see there very nicely how, as the water content increases in relation to the red compaction curve, you can see how the undrained shear strength is reducing. It's just two different test methods. And if you divide undrained shear strength by 25, then you would get an approximate value of the CBR. So the first point there, other than 50, you'd get a CBR of 2%. So this kind of information is very helpful when you're looking at trying to determine CBR for design. Now, just a few brief words about actually determining profiles of subgrade soils. How do you measure properties of your subgrade soils? Well, we tend to have site investigation reports with boreholes, which may have samples taken out and tested, and they may have SPTs, but generally the first tests or samples are taken to the depth of 1.5 meters, unless you've asked for special attention to be paid to the shallow soils. So perhaps of more interest would be things like static cone penetrometer tests, where we get a very detailed profile, and these instruments can be calibrated to give you CBR directly, or dynamic cone penetrometer tests, DCPs, also can be calibrated to give you CBR directly. These sorts of tests are very nice for looking at subgrades, partly because they're simple tests, but also because you get a very detailed profile in that upper meter or so, which is the most important part of the profile of the soils. And there you are. So you see two gentlemen there doing, in this case, is actually a static cone test, but just looking at the upper soils in a particular profile. Now, my last topic, and I've reached an hour, but I will get through this. There's a fair bit to talk on here, but it goes quite quickly. I want to talk about surface modulus testing, because this is, I think, very important, but also I think there is a little bit of misunderstanding sometimes. So we're talking about plate loading tests. You can see there, this is actually in conjunction with a particular trial that was carried out doing plate loading tests on subgrade soils. Those are actually soils with a CBR of about 2%. And also on the aggregate surface. Typically, these plates are normally with a 300 millimeter diameter, although we can use different ones. And it works like this. So if you look at a cross section, we apply a load to our plate and it goes down and you can see the dial gauge going around. Then we remove the load like that. And the plate comes up again a bit. And then we load again, a second loading cycle, and the plate goes down again. And that's a very typical procedure. 2 load cycles, you can do more, but this is very standard. And this approach is used a great deal in Europe. And I'll tell you a wee bit more about that in a second. So here's a typical result. So we had those 2 loading stages and we plot settlement of the plate against pressure. So the first stage in dark brown, unloading in yellow, and the next loading in the sort of gold color. And then what we would do, we would pick off a particular stress range, delta P, and settlement, delta S. And we use the formula you see there to give us the modulus. And this is a surface modulus, E. Call it E. It's a surface modulus. And you can see there, we need to take into account the radius of the plate and the Poisson's ratio. And this can be done for both the first and the second cycles. And you see it done there for the second cycle. And that particular formula you see there, it's an elastic solution for the settlement of a rigid circular area on a semi-infinite soil mass. Now, in fact, the EV1 and EV2 approach is used a great deal in Europe. Today, no time to talk to you about this in any detail, but one thing's interesting is that the ratio of the 2 is in some countries used as a check on compaction quality, because not surprising, if a layer compresses a great deal on that first loading cycle compared to the second, it probably wasn't very well compacted. So that's just something to be aware of. Now, sometimes you might see this expression. It looks almost the same, but slightly different, where you just have a 2 in front of it. The difference there, it's for a flexible, it's an elastic solution for a flexible circular area. So we don't use that one for the plate test. Here's a rather nice diagram that is correlating EV1 and EV2 values against CBR, both for EV1 and EV2. So EV1 in blue and EV2 in brown. The low values are cohesive soils and the higher values are for granular soils. And you can see quite a nice relationship. But also I've plotted on that diagram the resilient modulus according to the AASHTO relationship. And you can see that the resilient modulus is predicted to be quite a lot higher. And we're going to look at that in detail in a second. Now, here's an interesting question. If I do a test like this, a surface plate test, is it going to give me the same result as taking out a sample there and putting it into a triaxial test and doing one of those triaxial tests? Well, the answer is almost certainly not, for all sorts of reasons. If you have a perfect material, then probably you would get a similar result. But for surface load testing, we have the effect of the deeper layers. And that's also, so with the surface load testing, it's not the layer immediately below the plate you're testing, it's the entire sequence of layers. So I just want to look at that with some testing carried out by TRL. That's the Transport Research Laboratory in the UK. We're going to look at testing using what's called the falling weight deflectometer. Now, this is a method of testing which is a dynamic test. So rather than build up the load gradually by jacking against a reaction, you just drop a heavy weight onto the plate and you get a very short-term high load. And we can measure the deflection of the plate and use that deflection to calculate a modulus, which I've called EFWD, the modulus from the falling weight deflectometer. So how do they compare, EV2 and EFWD? Well, you won't find many studies like this, but there is one here, which I have, where testing was done like this on a 300 millimeter sub-base layer of a CBR of 2%. And you can see there a very nice profile of CBR measured using a penetrometer. And you can see there checking the CBR values through the subgrade material. There is the particular plate test, the picture we saw earlier on. So that was used to measure EV2. This equipment was used to measure EFWD. And then here is a relationship between the two. EV2 plotted against EFWD. And in this particular testing, if you look at the numbers, almost the same. Now, I don't know if that's always the case. They're going to be similar. In this particular case, they were, but it's probably useful to get more information about that if this is of importance to you. So obviously, the FWD is a much quicker test than doing a plate test. But you might need to know what is the static or the EV2 value. So that relationship could be useful. One more thing to look at of interest is the effect of layer thickness, something I mentioned earlier on. So in a particular trial, this was tested with 3 different thicknesses of 300, 450, and 600 millimeters, all over a CBR of 2%. And using the falling weight deflectometer, we have a modulus of 31.2 on the thinnest one, then 60.9 and 80.7 on the thickest. So you can see the influence of thickness on the measured surface modulus. It is significant, almost 3 times as you go from 300 to 600 millimeters. And we can examine this behavior using an elastic solution. So this is an elastic solution that predicts the settlement of a plate on a 2-layered system where you've got E1 and E2 of the 2 layers, the modulus values, and the ratio of the 2 is called ER, which you see on the graph there. And we can assess the settlement of the plate using that. It's actually the similar expression to the one we had for the flexible analysis just now, but you multiply by an influence factor. Influence factor takes into account the double layer situation. So, and we take into account the radius. So the horizontal axis of that graph is the thickness of the layer normalized to the radius of the plate. So thicker and thicker and thicker going towards the right. And the influence factor is the vertical axis. So basically, as the influence factor goes to 1, the thickness is becoming infinite. In other words, we go back to that original solution that we had earlier on. Anyhow, just to see what happens. So those are the actual plate deflections measured in each of those tests. You can see the delta values there. So if I now calculate the influence factor, the IP value, the influence factor, based on the actual test results for those 3 cases, I get the 3 brown symbols. And what's interesting is it's not predicting a uniform ratio of the modulus values. You might say, well, something wrong? I don't think so, because as the layer becomes thicker, the stresses in the subgrade soils are becoming smaller. And if you think back to that testing with the repeated load triaxial test, then for the lower stresses, we had the higher stiffness values. So I think it works out extremely well. Last part of this story, just a few more slides to go, is about still surface modulus testing, but now it's about cyclic testing. And this is using this incredible piece of equipment, which is called an APLT, Accelerated Plate Loading Test, developed by a gentleman in the USA. Now, that piece of equipment is pretty sophisticated, and I don't believe there are any sets of it outside the USA. But what's nice about this is that that piece of equipment can drive up along your pavement, jack itself off the ground, put a plate down underneath itself, and do all kinds of different plate testing, including cyclic or repeated load plate testing. And basically what you find is that the resilient modulus is only becoming constant after many cycles of load. So here's a nice little video. So that's the plate load test in action. So that's all being automated. So I'll just quickly rush to some very quick results of one piece of work. So this was a test carried out using the 300mm diameter plate over a thin base course, just 150mm over a soft clay. And the profile there on the right is CBR interpreted from a DCP test. And we measure EV1, EV2, and resilient modulus, all using that equipment. Now, I'd have to say, I'm not aware of this being done. I have never seen this comparison before. So for me, looking at this in detail to create this was the first time I'd looked at this. So I found this rather interesting. So there is the if you like, the static plate test result to measure EV2, rather like the previous curves I had. So EV1 from the first loading cycle, EV2 from the second one. Now, this is a maintained load test. So each load point takes about 2 minutes in total. So to reach the final pressure of what, 300, just over 300 kilopascals, takes about 12 minutes. And we measure, those are the values of EV1 and EV2. They're very low, not surprisingly for such a thin pavement over a soft clay. But also in that red box, I can put inside there the results of cyclic testing. Now, in the cyclic testing, each load cycle takes 1 second, much faster rate of cycling, and it looks like this. So you now can see the comparison of the slowly applied plate tests to do EV1 and EV2 measurements compared to the very high speed resilient modulus testing. And the modulus at the end of that, right down at the last few cycles of that testing, down at the bottom of that sort of black mass of lines, is 84.3 megapascals. So just to summarize, we have those modulus values, a large difference. But why is it so big? Well, because of the stress situations, because of the many repeated load cycles before you measure MR compared to EV1 and EV2, and of course the rate of loading. They all have an influence on that, in those results. And yes, I think I'm not aware of many correlations like this, but there is an example of some real data. If I go back to this correlation I showed you earlier on, the correlation of EV1 and EV2 with CBR, and if I plot that data with those circular dots against a CBR of 8%, which was roughly what we had from the DCP test, then you can see there is a reasonable match. But this graph is a correlation intended for subgrade materials. In other words, not layered materials. It's for materials that are infinite in extent. So it's not a perfect match, but quite interesting to see that. So I've got to the end. I'm sorry, I took a few minutes more than I intended to, but I knew there was a lot to talk about. So we've had a pretty careful look at geotechnical aspects of road pavements, and we've talked about index testing and the importance of the AASHTO soil classification system, which is a particularly good one for road pavement materials. Then we spent some time on the resilient modulus triaxial test, followed up by the well-known CBR test, and then some information about undrained shear strength and CBR, in particular, the profiles of these values. We finished off with information there about surface loading tests. And as I said, throughout that, we spent a great deal of time looking at different correlations between different values. I have by no means presented you with every correlation you can find between these various parameters, but we covered quite a few. I'm sorry I've been a bit over time on this particular webinar, but here is our summary. The September webinar will be a bit of a change of topic, and I want to talk a little bit about reinforced soil structures and 11 things you should know about them. And also to let you know, if you're interested, just coming up tomorrow, it's me again, I'm afraid, but I'm doing a shorter webinar about a program called Tensar Soil, which is looking at the design for earthquake loading and the serviceability limit state check. So I've come to an end. Thank you very much for bearing with me through all of those slides. And I will now have a quick look at questions. So